What is the quantum error threshold in computing? Have you ever wondered how quantum computers manage to perform calculations with such fragile quantum states? One key concept that plays a vital role in this process is the quantum error threshold. This threshold is the maximum error rate per quantum operation or per quantum bit, also known as qubit, below which quantum error correction can effectively detect and fix errors faster than they occur. This capability is essential for achieving reliable and fault-tolerant quantum computation. When the physical error rate in a quantum computer stays below this threshold, it becomes feasible to use error correction codes. These codes help reduce logical errors to very low levels. This means that large-scale quantum algorithms can run accurately despite the delicate nature of quantum states. Quantum error correction codes work by encoding a logical qubit into multiple physical qubits. This approach allows the system to identify and correct errors such as bit flips, where a qubit state changes from 0 to 1 or vice versa, and phase flips, which alter the phase of the quantum state. The threshold theorem states that, as long as the error rate remains below this critical value, the error correction process can keep pace with and correct errors faster than they accumulate. This effectively lowers the overall error rate in the computation. The specific value of the quantum error threshold can vary depending on the type of error correction code used and the noise model of the quantum hardware. For instance, surface codes, which are among the most promising quantum error correction codes, have estimated thresholds around 1% error rate per qubit operation. This means if the physical qubits maintain error rates below about 1%, fault-tolerant quantum computing becomes possible, although it requires a significant number of physical qubits, often in the thousands, for each logical qubit. Achieving an error rate below this threshold is essential because quantum states are highly sensitive to noise from the environment. This noise can lead to errors that quickly degrade computation. The threshold serves as a practical benchmark for hardware developers and algorithm designers. Only by reducing error rates below this level can quantum computers scale up to solve complex problems reliably. In essence, the quantum error threshold defines the boundary between noisy, unreliable quantum devices and those capable of fault-tolerant operation through quantum error correction. It is a foundational concept in the development of quantum computing hardware and software, guiding the implementation of error correction codes and the pursuit of scalable quantum technologies.